Hello guys, welcome back to the Kara Tutoring YouTube channel, or as Jeffree Star might say, hi, how are ya? So in today's video, we will be talking about special right triangles, a concept that can be found frequently on the ACT. I understand that we have not posted much content regarding the ACT, so I'll be starting a series of videos dedicated to the mathematics portion of the ACT. And I want to preface that I am not much of a YouTube content creator. I'm no PewDiePie or T-Series, but I'll try my best to convey everything that is relevant and necessary in order to help you succeed on the mathematics session. And feel free to include your suggestions or feedbacks in the comments below. So without further ado, let's get started. So what is a special right triangle exactly? So basically, special right triangles are a particularly unique class of triangles that have special characteristics that can be manipulated and utilized to solve many other triangles that have these similar characteristics. I know that makes no sense, but I'll be showing you on this handy dandy whiteboard. So as you can see, I have two triangles drawn, and these are the two kinds of special right triangles that you must remember on the ACT, and you will see them frequently as aforementioned. So I encourage you to remember these, and I think the ACT might have these on a reference sheet given to you, but just to be safe, just memorize it. So the first special right triangle, as you can see, has the angles 60, 30, and the 90 degrees. And keep in mind, all of these add to 180 degrees, a characteristic that is the same for all triangles, hence the name triangles. So, and then let's move on to the second triangle. And these have two angles that are the same, 45, 45, and then you have the 90 degrees. And because these two angles are the same, that means that these two sides are of equal length. And thus, this is a isosceles triangle versus this one, which is a scaling triangle. It has three sides that are all different. All right. And so you may ask, Stanley, those are all the angles, but what about the sides? Well, let me choose let's choose a blue marker for this, blue expo marker. So as you know, all triangles aren't created equal. So, however, all the angles have the same ratio to each other. So for the 30-60 triangle, you will have a 1 to square root of 3 to 2. For the 45, 45, 90 degree triangle, it will be 1 to 1 to the square root of 2. And another way to write the name of the triangle in number form is 30, 60, 90 triangle. And then this one will be the 45, 45, 90 triangle. All right, so what do these ratios mean? To best explain this, I'll give you an example. So we have here a 30, 60, 90 triangle. And let's say that this side is 6. So following the rules to this ratio, that means the rest of the sides will be 3 and 3 to the square root of 3. And I'll explain in better detail in just a second. So for the 45, 45, 90 triangle, let's use this example. Sorry, I can't draw shapes. That's why I failed kindergarten once. And let's say, how about this? We can do a 10, 10, and these two sides are equal. That means the hypotenuse would be 10 to the square root of 2. Okay, so let me explain this in more detail. Let me adjust this. Okay. So let's say that it is given that these are the angles, the angle measures, and we are given that the hypotenuse is 6 inches. So looking at this, I realize that this is a 30, 60, 90 degree triangle. So that means the rule of 1 to square root of 3 to 2 ratio will apply for this triangle. And I'm giving that this hypotenuse is 6 inches. So that means that this side will be 3. And the reason why I put 3 right here, not right here, is because this side is the smallest side. And if we look back at the ratio, it goes from smallest to largest. So this is the ratio of the smallest, this is the ratio of the middle length, and then this one's the ratio of the longest length. And as we the hypotenuse always, yes, always, it always has the longest length. So the 6 inches right here, and therefore the 6 inches is talking about the 2 in this ratio. And now we need to find the smallest length. And the reason why this is the smallest length is because it's directly across from the smallest angle. So in the 30, 60, 90 triangle, in this trio, the 30 is the smallest. So therefore, the smallest side will be the side directly across from that angle. And the second smallest will be directly from the 60, because 60 degrees is the middle angle out of the 3. All right. So this is a 3. So that means this will be 3 square root of 3. Basically, you multiply the square root of 3 to the smallest side. So bring the 3 right here and multiply by square root of 3. So let me do a red marker this time. Let me erase this. So let's say that we have for the sake of easiness, let's use all even numbers. So this will be a 20. So that means this side will be a 10. And this side will be 10 times the square root of 3. Pretty simple, right? So you basically divide this by 2. Here's 10. And then multiply by square root of 3. And as you can see, this is the smallest, this is the second smallest, and this one is the largest. This is smallest, second smallest, largest. All right. And here's how I remember this ratio. So basically write 1, 2, and 3 in a sequence. So 1, 2, 3. Add the square root at the end. That means it switches places because now square root of 3 is smaller than 2. So 1 square root of 3, 2. All right. And for the 45, 45, 90 triangle, that will just be 1, 1, 2. Because for 45, 45, 90, two sides are the same length. It's an isosceles triangles because there are two angles that are the same. So 1, 1, 2. Add the square root. And because the square root of 2 is still larger than 1, it stays right there. So that's how you remember it. So let's move on to the 45, 45, 90 triangle. All right. So as you can see right here, we have a 10 and a 10. The reason why we don't put a 10 right here is because these are the same lengths. All right. So these are the same. And then to find the third side, you just bring the 10 right here and multiply by the square root of 2. So let me give you a different example. Let's get out the blue expo marker. How about let's draw like this. Let's draw like this. Let's see. There you go. That's a much better one. So this will still be the hypotenuse because if you tilt this, see, this is the two legs and then this is the hypotenuse. So let's say these two sides have the length of 8. All right. So that means these two angles are the same. And they're 45 and 45. So that means that this side will be 8 times the square root of 2. Now, how do we expand from that scope into maybe a problem that requires the use of a special right triangle and not just, not like the example that I gave previously. So let's say we have an equilateral triangle. I'm bored of green. Let's go with blue. So an equilateral triangle has all three sides of equal length. So let's say one of the sides is 30. And we were just given this image. And so from this little tick mark right here, we know that all three sides are the same. And if that's not the case, they will probably have one right here. So that means these two sides are of equal length, and this one is a length of its own. So here's an explanation if you don't already know what that tick marks mean. I think they're called tick marks. But anyway, we were just given this image, and we were told to find the angles in the side measures. So since this is an equilateral triangle, we can automatically say all three have a side of 30. So the hardest part is finding the measures. But if we put our thinking caps on, we can go ahead and split this in half. And when we split this in half, let's put this on a Cartesian graph. And when we put this on a graph, this will create a 90-degree angle. And an equilateral triangle always has 60 degrees, 60 degrees, 60 degrees on each vertex. And when we split this angle in half, this becomes a 30 and a 30, right? So now we have two 30, 60, 90 triangles. Crazy, right? And since we already know this side is 30, this side is 30, that means the smallest side, which is this one right here, the 30 degrees, the smallest side will be 15. The smallest side will be 15, right? And then the ratio is 1, 2, 3, square root of 3. And we already used 2 and 1. So that means the next side, the final side will be 15 times the square root of 3, 15 times the square root of 3. Yeah, pretty awesome. So now I want to talk about Pythagorean triples. And it kind of goes along with what we talked about earlier with the special right triangles and how to find the sides when it's given that you have all these three angles. So what if you have a right triangle and you know that one of the sides is 3? Following the Pythagorean triple principle, that means this is a 4 and this is a 5. It just happens to be so that way. So let's solve it with this formula right here. A squared plus b squared equals c squared. So this is the formula that you would usually use to find the third length of a side. So let's say this side is 3 and this side is 4. And we're trying to find the length of the hypotenuse. So let's use this formula right here. So usually the shortest side will be A, the second shortest will be B, and the longest will be C. All right, so A, 3 squared plus 4 squared equals C squared, and a C is the X in this case. All right, so simplify. 3 squared is 9, and then 4 squared is 16, and you add these two together and you will get 25 equals C squared. And to isolate the C, we will do the opposite of the exponent, which is a square root. So square root then cancels, and you square root 25, and then the square root of 25 is 5. So that means X is 5. However, instead of going into all that mess, what we could do is to remember the Pythagorean triple, which is one of them is 3, 4, and 5. And since we were given 3 and 4, we automatically know that the third length is 5, because this is a right triangle. and it only applies to right triangles. And it doesn't matter what these two angles are. It could be like this or this. Sorry, I'm just exaggerating. But as long as there's one right angle and then one of the numbers is part of a Pythagorean triple, then you're good to go. So 3, 4, and 5 is one of the many Pythagorean triples. The second most common that you will see is the 5, 12, 13. All right. So the first one's 3, 4, and 5. And then the third most common will be the 8, 15, 17. But I just want you to memorize these two right here. All right. And you can always work from that. So for example, a 6, 8, 10 will be a Pythagorean triple because this sequence right here is this on steroids, or also known as multiplying this each number by 2. So 3 times 2 equals 6, 4 times 2 equals 8, 5 times 2 equals 10. And then you can multiply this by 100. So 600, 800, 1000. This will still be a Pythagorean triple, all right? 8, 15, 17. Could be 16, 30, 34. This is a Pythagorean triple. And you can multiply this by 1,000,000, and it will also be a Pythagorean triple. So the most common you will see are these two right here. And if you're not sure, you can always plug it into the equation. You can always use the Pythagorean theorem to find the sides of the triangles or fact check. And that is the conclusion to our video on special right triangles and Pythagorean theorems. If you have any questions, feel free to leave your question in the comment section, and we as a team will answer it for you as fast as we can. Thank you, and see you next time.